NASA is currently planning to land humans on the moon once every year or two under the Artemis program. But buried in their long-term planning documents is a much more ambitious goal: monthly lunar landings by the early 2030s. Not once a year, not quarterly, every single month, 12 times per year, putting crews on the lunar surface and bringing them back safely. And if you think the current Artemis timeline seems challenging, the engineering required to achieve monthly cadence is absolutely staggering. Because this isn't just about building more rockets, this is about creating an entirely new category of space infrastructure that has never existed before. Let's start with the most fundamental constraint: propellant. A single Starship HLS mission to the lunar surface requires approximately 1,200 tons of liquid methane and liquid oxygen to be transferred in Earth orbit before the lander can head to the moon. That propellant has to come from tanker versions of Starship, each carrying roughly 100 to 150 tons of cryogenic fuel per flight, which means you need somewhere between 8 and 12 tanker launches just for fuel one lunar lander. Now multiply that by 12 missions per year. You're looking at 96 to 144 tanker flights annually just for propellant transfer. That's not counting the lander launches themselves or any cargo missions. For comparison, Falcon 9's current launch rate is approximately 130 flights per year across their entire manifest, and that's considered an industry-leading cadence. To support monthly lunar landings, Starship would need to launch nearly 3 times per week, every single week, with no significant gaps for maintenance or failures. And remember, these aren't simple satellite deployment missions. Each tanker flight requires precision orbital rendezvous, cryogenic propellant transfer in microgravity, and absolutely zero failures, because a single lost tanker means the entire mission timeline slips. The propellant transfer itself is one of the most technically demanding operations ever attempted in space. Liquid methane needs to be kept at -162 degrees Celsius or it boils away into gas. Liquid oxygen has to stay below -183 degrees Celsius. In the vacuum of space, with sunlight heating one side of the spacecraft to +150 degrees and the shadowed side dropping to -150 degrees, maintaining those temperatures is brutally difficult. SpaceX's solution involves active cooling systems, multi-layer insulation, and specially designed transfer couplings that can move 100 tons of cryogenic propellant between two spacecraft in approximately 30 to 45 minutes. But here's where it gets complicated. Boil-off is inevitable. Even with the best insulation, cryogenic propellants will slowly evaporate in space. Current estimates suggest Starship loses approximately 2 to 3% of its propellant per day to boil-off. That means if you're assembling a mission that requires 12 tanker flights over 2 weeks, the first tanker to arrive loses roughly 30% of its propellant by the time the 12th tanker docks. You have to account for that loss by launching extra tankers, which drives up the total number of flights required. Some mission profiles now suggest you might need 15 tanker launches per lunar mission once boil-off is factored in. Then there's the depot spacecraft itself. This is a modified Starship designed to loiter in orbit, storing propellant and acting as a gas station for lunar-bound landers. The depot needs to maintain cryogenic temperatures for weeks or months at a time, which requires substantial power generation from solar arrays and continuous operation of cooling systems. It also needs autonomous docking capabilities to receive propellant from tankers and transfer it to landers without human intervention. NASA's current plan calls for at least 2 depot spacecraft in orbit simultaneously to provide redundancy. If one fails, the other can continue supporting missions while the damaged depot is either repaired or deorbited and replaced. Each depot has a finite lifespan. The thermal cycling from repeated propellant transfers, the mechanical stress on docking mechanisms, and the degradation of solar panels from radiation exposure all limit how long these vehicles can operate. Current estimates suggest a depot might survive 50 to 75 refueling cycles before critical systems start failing. At monthly launch cadence, that's roughly 4 to 6 years of operational life, which means NASA needs a continuous production pipeline of depot spacecraft, building and launching replacements on a regular schedule just to maintain the infrastructure. Vehicle production is another massive bottleneck. Each Starship HLS lander is a custom-built spacecraft with specialized landing legs, life support systems, and crew accommodations. These aren't mass-produced like Starlink satellites. Every lander requires months of assembly, integration, and testing before it's ready to fly. And unlike the tanker variants, which can potentially be reused after delivering their propellant, the lunar landers are one-way vehicles. They stay on the moon permanently or are discarded in lunar orbit after the crew transfers back to the Orion capsule. That means NASA needs 12 brand new landers per year just to maintain monthly cadence. The Space Launch System rocket presents its own challenges. SLS is required to launch the Orion crew capsule that carries astronauts from Earth to lunar orbit, where they transfer to the waiting Starship lander. But SLS currently takes approximately 18 months to assemble and prepare for a single launch. The rocket uses 4 RS-25 engines scavenged from the retired Space Shuttle program, and those engines are in limited supply. Boeing is building new RS-25 engines, but production won't reach the rate needed for monthly launches until at least 2029. And that's assuming no delays, which is optimistic given Boeing's track record on this program. One proposed solution is to eliminate SLS entirely and launch crews on Starship itself. This would require developing a crew-rated version of Starship with life support, abort systems, and heat shielding for Earth re-entry. Starship is already working on these technologies, but getting them certified for human spaceflight adds years of testing and qualification. The advantage is that Starship can potentially launch multiple times per week once it's operational, removing the SLS bottleneck. The disadvantage is that NASA would be putting all their eggs in one basket, relying entirely on SpaceX hardware for every aspect of lunar missions. Surface operations create yet another layer of complexity. If you're landing crews every month, you need infrastructure on the moon to support them. That means habitats, power systems, life support equipment, and consumables like food, water, and oxygen. Each landing mission needs to deliver not just astronauts, but also cargo, spare parts, scientific instruments, construction materials, and propellant for the lander's return to orbit. Current Starship HLS designs can carry approximately 100 tons of payload to the lunar surface, but a significant portion of that capacity is consumed by the propellant needed for the return flight. One solution being studied is in situ resource utilization, or ISRU. This is the idea of manufacturing propellant on the moon using local materials. Lunar regolith contains oxygen locked up in mineral compounds. Through a process called molten regolith electrolysis, you can extract that oxygen and use it as rocket oxidizer. Water ice in permanently shadowed craters near the lunar poles could be processed to produce hydrogen and oxygen. If ISRU systems can be deployed and made operational, they could dramatically reduce the amount of propellant that needs to be shipped from Earth, cutting the number of required tanker flights by as much as 60%. But ISRU technology is still experimental. The equipment is massive, power-hungry, and unproven in lunar conditions. A complete oxygen production plant would require several tons of hardware, kilowatts of continuous power from solar arrays or nuclear reactors, and months of setup time on the surface. And it needs to work reliably, because if the ISRU system fails, the crew is stranded until propellant can be shipped from Earth. That's not a risk NASA is likely to accept until the technology has been thoroughly demonstrated on multiple missions. Communication infrastructure is another requirement that scales with mission frequency. The moon rotates, which means any fixed ground station on the surface will lose line-of-sight contact with Earth for roughly 2 weeks out of every month. Apollo missions could handle that because they only stayed on the surface for a few days. But with monthly landings and eventual permanent bases, NASA needs continuous communication coverage. That requires a constellation of relay satellites in lunar orbit, probably 6 to 8 spacecraft, positioned to ensure at least one is always visible from both Earth and the lunar surface. These satellites need their own propulsion systems to maintain orbit, power systems to operate the communication equipment, and ground stations to receive and route the signals. Then there's crew rotation.
Monthly landings don't necessarily mean monthly crew launches from Earth. A more efficient approach is to station crews in lunar orbit for extended periods, maybe 3 to 6 months, with individual astronauts rotating down to the surface for 1 or 2 week shifts. This reduces the number of Earth launches required, but creates new challenges. The Orion capsule isn't designed for multi-month missions. It would need significant modifications to support long-duration habitation, including enhanced life support, better radiation shielding, and larger consumable storage. Or NASA develops an entirely separate habitat module that stays in lunar orbit permanently, with Orion just serving as a taxi for crew changes.
Medical capabilities become critical at this cadence. With crews working on the lunar surface continuously, the probability of injuries or medical emergencies increases dramatically. A broken bone, appendicitis, cardiac event, any of these could be life-threatening if you can't evacuate the patient to Earth quickly. The lunar lander needs medical equipment and supplies far beyond what Apollo carried. Telemedicine systems with high-bandwidth video links to doctors on Earth, surgical capabilities for emergency procedures, possibly even autonomous medical devices that can perform diagnostics and treatment with minimal crew intervention. And you need personnel trained to use all of this equipment under the stress of an actual emergency. So here's the bottom line. Monthly lunar landings require producing Starship vehicles at a rate of 15 to 20 per month when you account for tankers, landers, and depots. They require flawless orbital refueling operations repeated more than 100 times per year. They need surface infrastructure capable of supporting continuous human presence with ISRU propellant production. They demand communication networks, medical capabilities, and crew rotation systems that don't currently exist. The total cost estimates for establishing this infrastructure run somewhere between $80 billion and $120 billion over the next decade. Is it technically possible? Absolutely. Every individual component has been demonstrated at some level or is under active development. But achieving it requires production rates, operational tempos, and reliability standards that are an order of magnitude beyond anything the aerospace industry has ever accomplished. We're probably going to see NASA achieve quarterly landings by the early 2030s, maybe even monthly landings by 2035 if everything goes perfectly. But turning the moon into a routine destination with airline-like frequency, that's still decades away. Unfortunately, though, there will probably still be a lot of hardware development along the way.